All right, let's get started. Okay. So hello, everyone. Welcome to our computer vision workshop. My name is Zenkai. And yeah, so today we'll be identifying shipping elements in Freight Frenzy. Yeah, let's get started. All right, so a bit of analysis of this year's task. So our task is to identify the barcode. So I like to call it barcode, but it's really just either a duck or your own custom shipping element on one of those barcode tapes. Yeah, and assuming your robot will be right here, you can use your camera centered like here to identify, the shipping elements. Yeah. So one of the major ways you can get more points is to use a custom shipping element and to replace the duck. So yeah, that's pretty profitable. So I'm going to assume that you want to do it. You want to build your own shipping element either through CADing and 3D printing or just build it from scratch. So yeah, so to make our shipping element suitable for vision detection, we want to make sure that it's large enough so that it will actually your camera can actually capture it. Because depending on your camera placement setting, if it's not large enough, it might not actually be the camera's field of view. And we also want the shipping element to have a bright color and have a color that's different from the field components. Like you don't want it to be like gray, which because of course you don't want the camera to confuse it with the foam tiles. You don't want it to be blue or red because that will, the algorithm might confuse it for the barcode tapes. And yeah, just to make sure you don't want the shape to be like weird looking. Yeah. So 1 second. Okay. So I'm assuming since you're in this workshop, probably you're using your camera. So you have two common options. You can use your phone camera if you're using, say, a phone as your robot controller. It is, of course, if you use a phone, this will be the most accessible option. The phone camera will be hard to place or hard to angle. You might need like a 3D printed component, or you might need more time to somehow secure the camera onto your robot. Yeah, so that might be a bit of trouble. You can also buy a webcam, and you'll have more options to pick from. So yeah, and since most cameras, okay, so at least the one we bought have some kind of I guess joint that lets you like rotate it, so it'll be pretty easy to angle webcams and help you eliminate like unnecessary view of the other parts of the field. So we have a couple of tools that we can use, so actually mainly just two, but we have TensorFlow. So of course, FTC gave us the TFOD, the TensorFlow object detection, and they came trained with like a TF Lite model, and it's built in. Its accuracy kind of fluctuates from season to season. We haven't tried this season, but I'm assuming that's going to be like okay or mediocre sometimes, and the speed is not that great. So, and if you want to use a customized shipping element, you might not be able to use it because TFOD only lets you identify freights like boxes, cargos, and ducks and whatnot. And unless your shipping element looks very similar to one of those, TFOD probably just won't work. And in case you're wondering about if it's worth it to DIY, like to train your own TensorFlow model, it's just not worth the trouble. Your time is better spent like doing something else, like making better out of, let's say. Oh yeah, by the way, if you have any questions, you can put them in the form that we have. Oh yeah. And we'll answer them in a spreadsheet that will be given to you at the end of the after you submit the form. Okay. So, okay, another tool that we have is OpenCV. So OpenCV is a very powerful open source library that's dedicated to computer vision tasks. And it's coded in C++, so you'll know, and C/C++, so you know that it's fast. And it's probably a better option for us than TensorFlow since it's so customizable. And if you coded it correctly, it'll be very fast and have a very high accuracy. In fact, our shipping element algorithm almost never failed this season. And yeah, so we won't dive into the full scope of its capabilities here, but OpenCV will be enough for what we need in FTC. So of course, just to brainstorm some possible options, you can use tfod if your shipping element is like closely resembles like duck or cargo or box, but I would advise not to. Yeah, DIY. Yeah, again, it's not worth it. You have to train your own data set or try to find the one that FTC used to train their TF-Lite model. And do you think you'll really train it better than them though? Or is it really worth the hassle? Probably not. Oh, yeah, so I can, in case you're wondering how to use tfod for future, maybe it's not useful for this year, but what about the future? Maybe the tfod works better next year. I don't know, but I'm going to demonstrate how to use tfod. So you should first get the FTC robot controller, aka the FTC SDK from the GitHub website. One second. So GitHub FTC robot controller. So yeah, feel free to clone it with Git, or you can download it right here, download the zip, and you'll be ready to go. And you don't have to follow along, but feel free to. Go back to the slides. Yeah, so the first step is, of course, opening up the FTC robot controller package here and navigate to the code. And you'll find all the sample code in this at this level, package level. So you see FTC robot controller, Java, and whatever this is, and external doc samples. And you'll see right here, when you scroll down, there's a couple classes that's named concept TensorFlow object detection, and that's the tfod thing we're talking about. And depending on what camera type you use, you might want to, if you use a phone camera, then you can go with just concept tfod. Or if you're using a webcam, you can use concept tfod webcam. So we'll go with webcam here. So this is an op mode. So if you want to use in your own op mode, I recommend just first copy this code, and then we'll transform it into something that's more usable for like all op modes, assuming you have multiple autonomous programs. So we've copied that, and let's build some. Let's make a new class and call it tfod. Paste everything in. Yeah. So we can leave them. We can leave those constants the same. So yeah. As you can see, the robot, the tfod is capable of identifying a couple things. So yeah, so if you're using tfod, I'm probably looking for duck. And just and you do need to register on Euphoria. Just see if I can showcase here. There's probably a URL here. Yeah. So yeah, you do need to log in and register. There's not much to it. It's free. After you're done, you can they'll give you a license key and you can just place it here. And we can probably turn this function into the constructor of this class. So see, well, if you don't have enough time, then just remove all of them. It's not aligned properly. Okay. So yeah, so each recognition will okay, so the tfod variable is the actual TensorFlow object detection thing. So and when you get, so you can either get updated recognitions or you can just get recognitions, because when you call get updated recognitions and the recognitions or the scanning results didn't change from last time, it will actually return null. So unless you always keep track of it, you would actually want to just use get recognitions. And each recognitions will be, it'll just have the coordinates of the scanning results. So it'll be a bounding box. It'll be a box around the object that's being identified. So if if tfod returns nothing, or it returns like an empty list or null, then you know that it didn't detect anything. So actually, yeah. So this will be the constructor, and this will go inside another method. Oh, what shall we call it? Actually, yeah. So for the sake of saving time, we won't dive into like how to actually identify whether the results on the left, middle, right. So to show you how to like package into something useful. Probably not a good idea. Maybe put something like nullable or something. Yeah. So we don't need the telemetry. And for the sake of time, we're just going to return the first updated recognition, or the first recognition. Wow, my computer is lacking a lot. We'll close this. Okay. Yeah. And for the sake of time, I just initialize some recognitions. Never mind. Yeah, so I guess we can just. So this is basically, oh, you also need the hardware map, but you get the idea. Yeah. But maybe store the hardware map here. And yeah, now you'll be able to reuse this in all your autonomous programs. And you just have to do some processing with the list of recognition to see which side the shipping element or the duck is on. But yeah, now onto our actual listen to OpenCV. Okay. So yeah, so we have another option. So this one's a bit complex, but sometimes during a brainstorming process, you might come across like idea that's complex, but it seems like it'll work. And so the gist is that you try to run like contour detection. It's basically edge detection. So you're trying to identify like what edges are on, or what edges are like visible in the camera's frame of view. And if there's a continuous set of edges, then you know that's probably some kind of shape, right? And you try to add, you're trying to find if there's a possible bounding box around this set of edges. And if there is, then you try to find the center of that box. And based on the center of that box, if it's on the left, then it's the left barcode, and so on and so forth. So it potentially works, but it's probably hard to code. There is sample code online that teaches you how to do this. Yeah, but it's unless you don't have another idea, it's probably not worth it. So there is a simpler way, and it's actually, in my opinion, it's like the best way. So, but before we dive into like how the algorithm actually works, we'll do a bit of setup here. So, if you want to play along or test along, follow along, you'll need to place your camera correctly. So yeah, just make sure that all three barcode tapes are within your camera's field of view. And it's best if you align the camera with the center barcode tape, but if not, we can probably compensate for that later. But just make sure that all three barcode tapes are within view, or at least make sure that your shipping element is large enough that if the third one is out of view slightly, that your camera still be able to pick up maybe a part of the shipping element. So if you use a webcam, you can just connect it to the USB port of your robot controller, and on your driver station, config the robot and edit a specific config that you're using, and then scan for new devices. And the webcam should show up, and it'll be named by default to webcam 1 with the W capitalized. And more on this later when we actually code the algorithm. So of course we know that we'll be using OpenCV, but it's a bit more involved. So when you have an OpenCV pipeline, or its pipeline, it's basically an algorithm that processes some video input. So when you have this pipeline ready, it needs a video input, right? And we're going to get that video input because OpenCV, Android SDK or FTC is not just going to like very helpfully just give you the video input. You have to look for it. So unless you're willing to mess with FTC SDK APIs or Android APIs, you're better off just using an pre-existing some kind of helper library for that. So there is a library called Easy OpenCV that handles it for you. So it's a FTC wrapper around OpenCV and helps you connect to the camera and use that camera input for your own pipeline. So yeah. Okay, so we'll be installing OpenCV right now. And to install, it's pretty easy. You can just go onto the OpenCV GitHub website. And all the steps are laid out there. So we'll be using Android Studio, and yeah. So navigate to your team codes, build.gradle module, and you'll need the dependency line here. So 1 second. Scripts. Okay, team code. So you can just put that line inside this like existing dependencies block, and it'll work. I think yeah. So you need to remove both instances of ARM64v8a in build.common.gradle. So this push. Oh. That's weird. But okay. And these are the only two instances, by the way. So, oh, wait. Yeah, right. Okay. And that'll be it for Gradle script changes. And we can do a Gradle sync here. Or you can Control-Shift-A and type Gradle sync. That'll do the same thing. Okay, so now that the Gradle sync is done, we so if you're so you do need to download this a shared object file to your robot controller. So I don't know if you heard of ADB before, but you can use ADB to connect to your robot controller wirelessly. So just connect to the your robot controller's Wi-Fi, or and ADB actually. So you can ADB connect and 192.168, and if you're using a control hub, it'll be this IP, and if it's a phone, it'll be some other IP that I don't remember, but you can probably find it online. After you're connected, you can do ADB push and download this file. You have the file name, whatever file name this is, and I believe it's what. Emulated storage 0. Let's see, ADB push. Yeah, it was something like that. ADB push the file name and then /storage/emulated/0/first. Yeah, that is required for OpenCV to work, by the way. And yeah, that'll be it. Interesting. Am I connected? Am I connected to an agent? Yes. Okay, let me just reload this page. Okay, so it's working. Okay. So let's go ahead and just create a blank pipeline. So your all your vision algorithm processing stuff will go inside this pipeline. So my computer is very slow. We'll call it scanner. Okay, and so every scanner, or I mean, every OpenCV pipeline is also a child class of the OpenCV pipeline class, and you do need to define or implement the process frame method. So for now, we'll just return input. And yeah, this is a bare bone pipeline that does nothing other than just returning the input video frame. So what happens is that this is the okay. So yeah, what happens is that you have a camera input, and it goes inside this pipeline, and then the output, or whatever you return from that process frame method, goes on your driver station in the camera stream menu, or I mean the camera stream interface. So after we installed, after compiled and installed this onto your phone or control hub, go to the driver station, and there should be a on the 3 dots there. Go inside, and there's probably a camera stream option. And yeah, that will just, and this will just display whatever the camera sees. Okay. Oh, okay. 1 second. Okay, so our algorithm will, so the way our algorithm works is that it looks for a certain color, and then it'll try to identify like how much color there is in each of the respecting or each of the corresponding regions for each barcode tape, and then whichever has the most will win as the final barcode scanning result. So our goal in the our goal in filtering color is to like find pixels that match your shipping element's color. So yeah, so if your shipping element is green, then we'll find all kinds of green that's in your video frame. So because depending on the lighting condition, your camera might not pick up the exact color of your shipping element. So we want to find a range that's as wide as possible to get everything you can see. So, but you might be wondering, like, how do we define a color range? So, so there's a couple of color models available at our disposal. The most common one is Rgb, and before we dive into the 2 color models, so a color model defines how we can represent a color. So, for example, in the Rgb color model, you create a color by adding various amounts of R, G, or B, and yeah, and when you have the maximum amount of R, G, and B, you have white. There's also HSV, which is another color model, but it is defined on top of Rgb. So it's an like alternate representation of Rgb. So instead of just having 3 channels for each primary color, we have a cylindrical representation. So on the top, you have like radial slices, and each radial slice represents a type of hue. So all the colors in this slice belong to the same hue. So no matter your lighting condition and whatnot, you'll always pick up the same hue. So we'll be, as you can see, this might be useful because, yeah, so even if your environment has a different lighting condition, maybe it's too bright, or maybe the color temperature is slightly different, you'll still be able to pick up that green pretty reliably with hue. You don't have to care about the other 2 channels. Okay, so now, so the color model is, it's like a theory, and we need an implementation of that theoretical model of color. And sometimes you might conflate, or you might confuse Rgb with, you might confuse the color space for the color model, but there's like a slight difference. For example, the Rgb color model is says that you can create colors by mixing Rgb, right? But there's also color spaces that uses this color model, but in slightly different ways. For example, this one color in the standard Rgb, the Rgb values you see every day, like 0, 255, 0. And for example, we have a color that's 30 for R, 250 for G, and 255 for blue. But there's also another Adobe color space, or rather Adobe Rgb color space, that that defines the same color, but in slightly different ways. And Adobe Rgb has a wider range of colors. So you could say that maybe the color space is larger than sRgb. So yeah, there's also reference color spaces, which are like they define like basically all the colors that we can see. So every other color space is basically defined in reference to these like primary color spaces. So these color spaces include like CIE XYZ and CIE L8B, CIE Lab, I guess. But you don't have to worry about them today. We're only interested in like converting color spaces. So right now, your camera, or depending on the model, might give your camera input in like Srgb or Rgba. The A stands for alpha, it's like transparency. It's just another channel. We can also convert back to Srgb, by the way. So as we've previously seen, HSV is pretty useful for identifying a specific type of color, like green. So if you're looking for green, you can probably just cut this slice right off and just look for a particular range of hues. But if your color is slightly, I guess, varied, like orange or whatever, and you're not bothered to find the exact, or you have this exact RGB value, but you don't know how to define like a range for it, because it is it's pretty, I guess, tricky thing to do in RGB. Then you can just go for HSV. You only have one channel to tune, just the hue. You can just find this. You can just look for colors that belong to this slice. So we'll convert from RGB to HSV to make our life easier. So to explain a bit more about HSV, so HSV is a color model that's defined in reference to the RGB color model. We've already talked about this. But like RGB, HSV also has 3 channels. So they're hue, saturation, and value. Notice how they're not like actual primary colors, or they have nothing to do with colors. They're just attributes of a specific color. So hue will be, I'll think of it as like a general category or type of color, like red or some other variants of red. And saturation is like the amount of color there is. So if you go low on saturation, then it'll appear like gray, more gray because there's less color. And if you go full saturation, then there is, it will be the richest color you'll see for that particular hue. And value is also associated with brightness. So yeah. So how do I say? Okay, so value is commonly associated with brightness, but so HSV is not a perfect representation of how humans represent, or how humans perceive color. So there is a concept called lightness, or I think luminance. And when you change a particular color, the value might be the same, but sometimes when you change a particular color to something else, the value in HSV might stay the same, but you might perceive it differently in terms of lightness. So it's not like perfect, but we don't care about the value channel, so it does not matter for us. So all these previous slides are just additional information in case you're curious how this works. But we're mainly concerned with the color space conversion from Srgb to HSV, and we'll get what we want. You also have some alternatives, of course. Of course, you have RGB, HSL. So the L stands for, I think, lightness or luminance. I can't exactly remember. There's also YUV or YCRCB. But you can consider, so sometimes for a particular shipping element, shipping element color, one of these will be better suited for that color, but HSV in our case is general purpose and suits us pretty well. So yep, after we find out how to define a color range, we can begin filtering for or searching the image for that particular color. So for us, we're using, I think, Logitech C270 webcam, and when we plug into the robot controller and we run OpenCV on it, it says that we're getting Rgba from the input frame. So we have to, there's no direct conversion from Rgba to HSV, so I have to do a 2-step conversion. From Rgba to Rgb, then to HSV. So we're actually, we'll actually code it right now. So we in the process frame method, we're basically getting an input frame, and we do some, of course, we do some processing with it, and then we return an output frame that's displayed in our driver station. And we want to keep this intact so that we can do something with it later. So we're going to create another mat. That's like our working variable. So I chose to have the mat variable created as a field, so that we are not like repeatedly creating mats that might cause memory leaks. So the first step is to use the image_proc.convertColor method, and you have a source matrix. So by the way, mat stands for matrix, and it's basically a 2D array but each element of that 2D array is a color. And we need a destination matrix, and that will be the mat we just created earlier. And we have a code. The code is basically like the operation that we want to do, like Rgba to Rgb, for example. Wow, my computer is really slow. To Rgb. Yeah. And do another step. We have this, and from Rgb to HSV. And you can use the same variable for input and output. That's fine. Or yeah. So now we have our color in HSV. We want to filter the color in actuality, and so we need a set of bounds. And if the pixel is within the set of upper and lower bounds, then we'll consider our shipping element's color. So to do this, I recommend you to take a picture of your shipping element if you have it designed already, hopefully, and use a color picker, or use a color picker online and try to identify like what color your shipping element is. Or actually, you don't, like practically, you don't actually need to do that, because so earlier I've said that you want to find the widest range possible. So you can just go ahead and use a HSV color picker, and say your shipping element is green. Let's see if this works. Yeah. So say your shipping element is green, then we will just go for the widest range possible. Let's see, we can stop here. So that's 69 degrees. You put it down, and then yeah, and the upper bound is 156. That down. Oh, so yeah, 1 second. So these are our H upper bounds and lower bounds, and one thing that you have to like be very careful about is that in OpenCV, the hue channel is divided by half. So instead of 0 to 360 for the full circle, you actually scale down by half. So this will actually be 69 by 2 and 166 by 2. And for the other two channels, however, we have S and V. They don't really matter. So you can just honestly just put some random lower bounds for these two channels, and it work fine. Oh, crap. Yeah, so 0 to 180, 0 to 55, 0 to 55. So, oops. Yeah, so 100 is, I think it works for us, And if you're having any trouble identifying the color based on your due to your like lighting differences, maybe sometimes your field is just too dim to see the element. You might want to like decrease this value lower a bit. But for our purpose, we can start using this now. So what I would do is I would actually define those two bounds as variables for increased code readability. Upper bound. So scalar is what you use to represent a color in HSV. And in the constructor, you can basically just go for, yeah, so each channel goes in order into one of those, I guess, arguments. So we'll go with the lower bound first, and yep, and actually that's not the upper bound, it's supposed to be lower bound. Okay. For the upper 156. And make sure that you're doing a floating point division, because otherwise you're losing some data. Because yeah, when you do interdivision, it'll actually truncate, and you're not getting like accurate decimal place and whatever. But it doesn't really matter here because you don't have to be that precise. Like most of the case, the color that the camera picked up probably fall like somewhere in the middle of this range, so you don't have to worry too much. Of course, we recommend like picking like a simple color, like just bright green for vision detection. And yeah, the next step is actually to use those bounds on this mat. Yeah, so we'll use the core.inRange method to import it first, I guess. Yep, so it needs a source matrix, which is mat, lower bound, and we need an upper bound. And can keep using, you can just keep using mat as the destination. And the inRange method basically goes through all the elements or all colors in the, I would say actually all pixels in the mat, and in the output for each element in mat, it'll create I guess a single value. So the resulting matrix will be a single channel image, so you won't have HSV anymore. It will just be like a grayscale. So if the original pixel match or falls between the upper and lower bound, the final matrix will have, or that final element, the process element will have a 255, and if not, you'll get a 0. Whew. So yeah, let's go to the slides. Okay, next step, we'll have to divide the camera input into 3 regions because we have 3 barcode tapes. So for our purposes, we can just, so assuming that your camera is angled down, it won't be able to see other irrelevant field or field elements or your competitor's robot, whatever. So we can just assume that everything in the frame is either the foam towel or the shipping element or the barcode tape. So we can just go ahead and divide the field into, or divide the video frame into 3 equal parts. And yeah, just 1 second. So we do need, so before we do that, though, we do need to define a few, I guess, boxes that, so second. So basically just do that, and yeah, so, and we need to define each of the individual rectangles. So since they don't really change from frame to frame, you can define it here. You need to use OpenCV one. Okay. But and we call these regions regions of interest, ROI. And we only need two. Yeah, we only need two points to define this rectangle, the two diagonal points. Either one is fine, I think. So how I interpret it, I think. Okay, so yeah, 2 points. Yeah, make sure you import the right point and rect classes. So let's just assume that the width is 320 and the height is 240, and that's the default parameters that's given by the, I guess, the easy OpenCV tutorial. And you don't really need high resolution because that's going to cause like much higher like computation. Yeah, that's going to take a lot of computation, and you don't really want that. And 320 by 240 is like good enough. And yeah. So I think oops. Let's say let's say the first one is on top, the second one's on the bottom. So X B. Yeah. Okay. So the first X will be 0. So, and let's just move that. Okay. Yeah, first X will be 0, Y will be 0. Second, yeah. So this will be whole thing is 320. 3 times divided by 3. Actually, it'll have to be a decimal. 3 or 5. I think it requires except doubles. Yeah. Okay. Yeah, the full height. Okay, the second one, the middle one starts here. And that's basically 320 divided by 3. Sure. Second one ends at 2 times 320 divided by 3, comma 240. So yeah, the X values are the columns or the, yeah, so this is X. This is Y. And they're both 0 here. Yeah, that should be fine, except resolve. Shrek, please. That's weird. not import the right class. Okay. Yeah, those are our three rectangles for our regions of interest. And to divide them up, there is a convenient method called subnet. So let's define those submatrices here. So map.submat just uses the rectangle we pass into it as a tool to carve out the particular region that we want. And do note that these share the same memory. So yeah, so these submatrices shouldn't cause like additional memory, I think. Okay, so now we've got our three submatrices. Okay, so if you have any misalignments, so say your robot, let's say your robot is okay. Let's say your robot is placed here, and that's the camera. Not very pleasing. Go say that's the camera, and you have three barcode tapes labeled that way, right? And you know it's not completely centered, and you can just use a number line to figure out like where they are placed in proportion from 0 to 1, and adjust the x by that proportion. So instead of doing like 0 or like did I do something? So yeah, instead of doing 0, 1, 2, maybe you can do 0, 0, 0 0.2, 0.7 or something like that. Yeah. Okay. So now we have three matrices, right? And they're all like grayscale images. So if the pixel is white, that means that is the color we're looking for. So we're basically finding like how much whiteness or how much we're basically finding how much whiteness there are in each of these matrices, and whichever has the highest value, that matrix win. And yeah, so we can we don't have to do like anything like averaging or whatever. You can just add all the values up, and since the matrix since the matrix is small, I don't think it will cause any overflow or whatever. So let's go ahead and do that. Double left value, and there is a method called there's a method called sum elements. So that will return the sum of all the pixels and divide it into 3 channels, of course. And yeah, and we're only interested in the actually since this is a grayscale image, only have one channel that's of value to us, so we'll use the first element of the array. So part code. yeah. Okay, so yeah, the next step is so now we have those values. That's basically like how much whiteness or how much matching color these matrices got. We can try to find the maximum of them by calling math.max. So by default, the max method only works on 2 elements or 2 parameters, variables, whatever. But you can basically divide and conquer and find the maximum between maybe these 2 first, and then whichever wins, compare that to the left value, and then that'll be our final answer. Yep. And yeah. So we can basically check or compare which one is the max value, and that will be our actual barcode scanning result. Actually, yes, is it not eligible? Oh, yeah, it's not eligible. So yeah, we can just use if statements. So if it's equal to the left value, we'll do this, and so on and so forth. Okay. So, so now that I've got our answer, we want to make sure that the autonomous mode actually, or your autonomous program actually know what the barcode scanning result is. And so since this method is run by, let's say, for simplicity's sake, it's run by your camera and not by your actual off mode, you'll have you won't be able to directly return the result in this method because your method or because your autonomous program did not directly call this method, and because the return type is mat and not something like string or int or some other enum. So you do need to save this result into this class and retrieve it later. So we won't be using int or string, and we'll be creating an enum for that. So in case you haven't heard of an enum before, an enum is basically a class, but actually I should have created enum instead of class. It's like a class in the sense that they're all like you can create objects from it, and you'll have a constructor. You can define methods for them, etc. But you can only have like you can only choose from a set of values to assign to each object. So where's the let's call this barcode. So there are only a few options. We left, middle, or right. Oops. Or if you prefer, you can call it like top or middle or bottom. I think it's the other way around, but I'm not sure. But you can use it to represent the actual barcode or the tier of the shipping hub that you're going for. Yep. So there's that. So we can also create a private barcode. And we'll set it to null to like signify that we haven't got a result yet when we initialize. So now we can save the result in our process ring method. Yep, and so do you need a getter for that? try and go with public. And I'll get barcode and it's all the same. So we're almost done here, but there I do have like a bit of extra content, and yeah. So let's create actual op mode. So, oops. Okay. So initialize. We do need to initialize the camera and actually use this barcode scanning pipeline with the camera. And the code is on their website. So let's just go ahead and check their sample code. So we'll be assuming that you use a webcam, but there is also like sample code for what's the internal camera or your phone camera. Okay, yeah, so these will be our code to use to initialize the camera. So yeah, we do need a variable or field, and yeah, no, we don't need to initialize it here because we need this code to initialize it for us. Okay. For every red line, just press Alt Enter, and Android Studio will import it for you. And we are using our own scanner pipeline here. Tonight. Yeah. And just for cleanliness, delete the comments. But and of course, if your camera is in a different orientation, you need to change this argument. So there are a few options: upright, upside down, sideways left, sideways right. So these are for if you're using a phone and you're tilting it sideways. Okay. And we won't do any error handling here. So you can, of course, change the resolution that's going to use, but I think the default is good enough. You don't actually want high resolution because that's going to cost like higher memory usage. And yeah. Yep, and that will start the camera, although asynchronously. So can wait for start, and we're gonna and we can just use the result that we get from the pipeline. So the camera automatically start the scanner once the webcam itself is ready. So you don't need to save this scanner. I think there's a method to get the pipeline, but we don't really need to. Okay. dot get result. So it might be asking what would happen if you don't the camera didn't open on time. Maybe you press start too early. So what we can do is we can wait till the vision algorithm actually finishes, or the first method call actually finishes. So we know that if the barcode is null, then we haven't run the algorithm yet. So we'll just wait on that. And we have an empty loop. So it'll warn you that this is basically waiting or whatever. But it's okay in this context. But if you want some better, if you don't like that, you can of course use like a countdown latch. And yeah, basically what happens with a countdown latch is that you'll have a countdown latch and you're going to start it with a count, let's say 1. And then if you're in your algorithm, you'll say that when your algorithm finishes, it's going to count down by 1. And your code is going to check here whether that count has decreased to 0 or not. Since we only have 1, if it's 0, that means the algorithm has ran. And if it's 0, then we'll return whatever result we have. And that won't be labeled as busy waiting because it's asynchronous and it's Java multi-threading magic. But this is simple enough and it works pretty well. Where's our autonomous? And now you can do whatever you want with the result. Yeah. Okay, so I think that's and we can you can also add some telemetry to help with debugging, but what time was that? I guess we can do that. And so we do need to pass in the telemetry object from the auth mode. We'll do different ways together. So this time we need a constructor for the scan. Okay, and now we can use it in our these branches and print the result. So actually we can just do it outside the branches. So telemetry dot add data barcode, and you can just convert whatever result you have to a string and then go lowercase. So to string to lowercase. It's a capitalized case. I guess not. Okay. And the update. If you want, you can also record what values you got. Okay. Yeah, and yeah, okay, that's it for telemetry. And you can also have some annotations. So annotations is what you do to you can draw like rectangles or circles or even maybe add tags. I don't know if that's possible, but that's a potential option. But you can like change the input matrix to add some data that will help you like visualize what's the result of the of your algorithm. So what our team does is we have like 3 rectangles around the ROIs, and if the result is matching, or if that ROI matches the barcode, then we'll just draw a green rectangle. Otherwise, we'll draw a red rectangle. So what you can do is we have match. So we call the green color the matching color, the match color. And I think it's in Rgba. Do you want it to be? So let's keep. Yeah. Let's convert the input to RGB, then convert that into HSV into matte. So we can don't need 4 channels. Okay. So match color will be green, R equals 0, and green equals 55 and whatever. And scalar mismatch color will be red. So yeah. Do I need anything? I'll do this stupidly. Okay. So okay, there's a you can draw a rectangle using this image proc dot rectangle method. I'll draw it on the input, and we can pass in the .i. Match. Okay, so that should do the trick. And yeah. So after you use the webcam to get a barcode into pass telemetry object. Okay, so after you use a scanner, the scanner is basically useless. You won't need it in the future, unless you do some wacky stuff. So after you get the result from the scanner, you can basically you want to like close the camera because that's going to cost resources. So we should define a method to stop camera stream and just close it. What's wrong with my computer? Let's stop. Actually, the webcam is the webcam is stored outside of this class, so yeah, because for ours it's stored inside for convenience, I guess. So we can after we're done, we can just stop the camera this way. There's a stop streaming. Okay, yeah, that should be good enough. And I hope results are enums defined. Okay, never mind. Yeah, that should be good. So this is basically our final section. So if you have more complex ideas in the future for OpenCV, you can use what's called grip. So grip is the URL. Okay. So grip is what FRC, or it's a tool made by FRC to help with OpenCV vision pipelining. And yeah, it's very convenient. You can build and test your computer vision pipeline at the same time. So you can download it here. I'm gonna put it in the chat. Okay. So yeah. So we can probably build it. So it's pretty convenient, and yeah, we do have enough time left. Okay, so you would start with an input, which is so if you don't have a webcam connected to your computer, you can just use an image. I'm gonna start with an image. I don't have an image handy though. I guess these are. I guess that's the image of our robot controller, but doesn't matter. So in order to build our pipeline, we can just use, so we start with a conversion from Rgba to Rgb. So we use CVT color. Yep. And, oh gosh. Wow, this is pretty annoying. My God, I'm just getting trolled. Oh, why is on top? Wait, no. Rgb to okay. So you can drag the source into the source option, and then drag the destination into the second block's source. And the second block is Rgb to HSV. Okay. Yeah. And the third option, I think, is I'm sure if there's some matrix. But oops, maybe there's not a submatrix or like submatrix option. Yeah. Let's do some live Googling. So imagine it doesn't do submatrices. This is kind of awkward. Okay, that is pretty limited. Or maybe I'm just not familiar with the tool enough, but yeah, I guess at least if it can't do anything, or if it can't do everything that OpenCV does, at least you can use part of it to test your pipeline, like live when you're building it. So it's still pretty handful, and you can actually build it each step, right? So yeah. So yeah, most of the common processing methods are here, but maybe the like the mat child methods or the mat methods are not here. Guess that's, yeah. Oh, but that's just scaling to scrolls. Yeah. I'll define it for itself, or it's just not here. But yeah, but that's, I hope you get the point. It's pretty valuable tool if you have more complex algorithms and you want to debug them. So I think that will be it for our workshop. So we get questions, probably hope they're already answered by one of our teammates. So let's check out the document. Okay. Yeah, our meeting is recorded, and Pixie. Yeah. Whew. Okay. If you have any questions, feel free to just unmute, or you can also put in the submit in the forum. But yeah, that is it for our workshop. So thank you for coming. Hope you learned something today. And yeah. No, feel free to leave, by the way. There will be a GitHub repository with the code, and our GitHub account is github.com/wolfcorp_etc. And we'll probably also release our own code very soon after this season ends, or not if we actually qualify. But so. Wait, you got it? We'll wait for a few minutes, and if you don't have any questions, yeah, feel free to just leave. We'll upload our YouTube video or our meeting recording on our YouTube channel, and just Google Wolfcorp FTC on YouTube. What?
There are people still there?
Okay, so we do have to end our meeting like soon. So if you don't have any questions, actually, yeah, if you do have any questions, you can just submit it on the forum. We'll monitor it after for like 4 minutes. But if not, we're just going to end the meeting right now. So thank you for coming and goodbye.